So web had all these problems where basically everything was wrong basically. The authentication was not working, the encryption was not working, all kinds of attacks, very easy, trivial attacks. And so they fixed it using this standard called 802.11i. The only problem was the fix would require changing the hardware, because if you were going to use AES, you cannot do that so easily in the software, and then so all of this stuff. So then they decided to have an intermediate version. So this was called WPA2 and RSN. In the book, I don't know whether they use the word WPA2. They use RSN all over, but basically this is popularly known as WPA2. I looked up in my own computer here at, for example, WFI is just WPA2, doesn't say RSN. So I have not seen the word RSN in the marketplace, but the book talks about RSN. WPA is basically a step, a transition part where you could change just by a firmware upgrade, which means you just go to the manufacturer and they will say new driver, which will simply change it from WEP to WPA. And so they did that, and in WPA basically what they do is they still use the same RC4. However, each RCA4 key is different. Previously what they did was they did use the master key for every packet, same master key. So it was very easy to do replay attack. Now with this one, they have per packet key. So even if your master key is same, your packet key would be different. And so RC4 encryption would be better. And then they replaced the CRC32, which was basically useless as a cryptographic hash function, because you can very easily compute CRC32 of the changes. CRC32 is very linear in the sense that if you take a number and divide by this polynomial, you get the remainder, that is one CRC. You change the function and divide by the polynomial, you get another CRC, and both of the CRC will be exclusive or of the difference of the messages. So they are just basically, if you exclusive are the messages and exclusive are the CRC, if the exclusive of CRC is 0, the messages can be replaced very easily. So you can take any two valid messages and exclusive are them, and this will not detect that. So that was so that they replaced with something else called MIC, Message Integrity Check. Now whoever came up with this name, MIC, also named, and I don't know what is the story behind it because I couldn't find anywhere any write-up on this, the algorithm is called Michael. So, and it's not an acronym, it's the name, so it must be some favorite name of some person. So the Michael algorithm is used to find the MIC. And so that is that, and then sequence number is used so that you cannot replace. So all of these things make it really strong enough for general usage. But if you have worked for the military, government, or or you really want something, then you move on to WPA2, which will require buying new hardware, like buying new laptops, things like that. Okay. Now, what is in WPA2 though? WPA2 actually, obviously has all of these in the sense that it has per packet key, and it has sequence numbers, it has 64-bit integrity check, but doesn't use RC4 and doesn't use Michael actually. It uses this one for the Mac, counter mode with cipher block chaining. So we have already seen that. Basically, you all know what is a counter mode. In fact, there might be a picture later on. So you put a counter, you encrypt it, and then you exclusive are that with the message. But cipher block chaining, so you take the cipher text and chain it, and then you take the last block and that becomes your hash. So that is the hash function, and then for encryption straight AES. In fact, even here AES is used because basically counter mode means you take the counter and you encrypt it using AES. You encrypt the counter. Here you encrypt the message. Oh, sorry, this also is with counter mode. So here also you encrypt the counter and then you do it. So this is all described in the next slide or so. But before we go to that detailed description, there are 5 phases. Phase 1 is finding the IP. Second phase is authenticating. Third phase is key negotiation. Fourth is then data transfer and then disassociation. And okay, all right. So the discovery phase is the only thing which is in clear. In the discovery phase, the station may send a probe, or basically, or it can listen to the broadcasts and then send the null authentication request, one of the two. So basically, there are two ways to find AP. One is that the AP is broadcasting every few seconds, and the stations listen to all the broadcasts and they decide, well, among these 10 SSIDs that I'm listening, the best one is this one. And you can program that best one in your computer. Does anybody know how to program the order of the APs in your computer? Huh?
You just do it from like the wireless. It depends on the
Yeah.
You just do it from like the wireless networks.
Right. So if you go into your network properties and you go into the wireless properties, it has a list of all the access points it has heard in the last 2 years. Okay? And it has an ordered list. And you can remove some of them, like if you went to a hotel for a day and then that is there for the next 2 years. I mean, it's not 2 years, it's just for life, until it probably overflows the list. So you can move some things up and down, and so that way it will try the top one first. And so then it says, okay, may I join please? And for some SSIDs, you can say, please try to join this even if it is not announcing. All right, so that is also in that same thing you will find in Windows, and I'm sure similar things in Mac. So if you want to join something which is not being announced, you can send a probe, and if somebody is there, then they'll say, yeah, you can join. Then you say, well, how do I authenticate? And so the response will come back, all right, you are rejected, but use this authentication method. Then you send that authentication method, and then you get that response, and then you can send request again. So basically, the first thing is that the discovery and association or authentication is two-way. Previously, in the beginning, we never authenticated the server in wireless, and we never authenticated the bank in the normal transaction. Right? The bank authenticated us, but we never authenticated. Today, now everybody has to authenticate everybody else. Right? So you authenticate the bank, as I said. Similarly, here we will have mutual authentication. Confidentiality and integrity. So for capability negotiation, this is where basically this comes up with the encryption algorithms, integrity algorithms, authentication methods. These are the ones I support, and then this will select that and send them. That's strange. So somewhere there is missing here. Maybe in this message, in one of these messages, the STA sends the list, and then the final message. In this message, access point will send back what it likes. So the final decision is access points, not the stations. And that's why I said it's strange, because if the station selected this, then they could really select the weak one, right? And they could play games. So even though both of them have to be authenticated, generally we rely more on the server to be right? So the server will do the final selection. So when it says that it will select one of these, WAP, TKIP, CCMP, vendor specific, for authentication will select A22.1xp shared key. So the initial list will come from the station, and the server will say, sorry, I cannot accept WAP. Right? Send me WPA request. And the station will not be allowed to join unless it says WPA. So basically it will take the minimum that it is allowed by the manager, by the administrator. So actually, the details are not on the slide, but basically, and this is what I think is this message contains the whole list from this side, and this message contains the selected list from that side. So secure association request has all of the same things, but whole list here, this set, and this one is one individual one here. 802.1x we already talked about, but I put this slide just for the sake of completeness. That 802.1x, what it does is it doesn't let anybody get onto the network until they have been authenticated. So if you are coming in from here, this happens on both wired and wireless networks now. If you're coming from here, you are connected to the authenticator only. And once you have authenticated, then the switch is closed, and then you are connected to the network. Sorry, this one says, all right, I made a mistake. It says external device. So this is where you're coming in. You can talk only to the authenticator and not to the network. And once you're authenticated, then you can talk to the network. So network is on the other side. And again, this is a repeat of the previous slide for completeness. And one thing I should do here is change everything to EPOL. So everybody knows the difference between EAP and EPOL. EAP is the general protocol which was designed for any link including PPP. EPOL is designed for LANs, and this is a LAN. Wi-Fi 802.11 is a LAN, so it uses EPOL. And so the only difference between EAP and EPOL is the initial header. So it will have a LAN header, and then that extra field called type or miscalled type. And then, so this one will say associate. So this will say, please tell me your name. Then we'll say, okay, here's my name. Then we'll go to the authentication server and say, well, here's the person I want to authenticate. It will send that challenge. Please ask them to do this challenge. Here is the response. Response will go to the server, and EPOL success will come back. All right. Now, so this can use any method you want. Right. It could be any authentication method that you like. It doesn't have. So why do we use EPOL here? What does it buy us? Anybody knows? Or why do we use EAP or EPOL here in the access point? Nobody has an idea? How many people took the exam? Yeah, you should have read this stuff in chapter 23. We talked about that the advantage of having EAP is, what is the reason for having EAP? Huh? No, basically the authenticator doesn't have to know anything. Only thing it needs to know is this one code, 3 or 4. What is the code 3 and what is code 4?
Accept and reject, right?
Yeah?
Accept and reject, right?
Yeah, that's all, success or failure. So basically it doesn't really know that you're asking for AES or you're asking for Al-Gamal, it doesn't really care. Whatever the server says, it sends it to the user, and whatever user says, sends it to the server. Only thing it reads is the type message, right? The code in the message. If that code is success, then you are connected. If code is failure, then you are rejected. And so that is the whole purpose of this whole exercise here, 802.1x as well as E whole lecture I made up was for this purpose, so that now the access point can be simpler, because you have thousands of access points on the campus, and you don't want to put all the passwords and everything in each access points, or you need to know them, or you want them to know all about every single encryption method that has been made. So all of that complexity is put in the authentication server. All of that secrecy is put in the authentication server. And the access points are totally, basically, simple devices, and if they get stolen, no problem, nobody gets any secret. Right? They have no secret, they see no secret, they know no secrets. They don't know the password, they don't need the password, and they don't store the password. They don't know so all of that. So the thing is, and access points are really accessible, and if you really looked around, worked very hard, you'll find the access point here, and then you can just take home. Right? So they are vulnerable. I mean, in this sense, I don't know. I mean, it's not that difficult, right? So that is the whole advantage of EAP. Is that clear now? All right. Actually, that is already written here. Authentication method can be changed without upgrading the switches and access points. So this could be an Ethernet switch in the normal wired Ethernet, wired networks, or access point in case of wireless thing. And so they are like security guards. I mean, I've shown you a picture of security guard. You go to a company, right at the front desk there is security guard sitting, right? And they come by the day. I mean, next day there will be another security guard, and there will be next day another security guard. So we cannot give them the secrets. They are security guards, but they don't have no secret. All they know is how to enforce the policies of the company. And the policy of the company will, basically is that you show them your badge, they put it under the scanner, and yeah, it looks good. The scanner has all the complexity, right? So this is the same way. At the airport, you go to the airport, there's a guy checking your driver license, has no security knowledge and has no security except that he does know how to read that. Actually, they do it manually. They used to do manually, but at latest time I went, 2 days ago, they don't even read manually. They just slide it through some machine, your driver license. And so basically these are guards, but at the same time they have no secrets. All right. So now the key, and please listen carefully to this slide and understand this carefully. This slide is not in the book. So whether you are using WPA, which is this one, TKIP. TKIP is the name of WPA. This is the IEEE name for WPA. TKIP stands for temporal key, some protocol anyway. It is in one of the slides later on, and CCMP is that counter mode. So this is your WPA2. And in both cases you need certain keys, lots of keys. And the key sizes may be different, and the book has a typo. I think the book said here it is 256-bit for temporal encryption key, and I double checked in many places, finally settled on 128-bit. So correct that typo in the book. In the book there's a table of all these keys, and in that K table they put 256-bit for TKIP and 128-bit for CCMP, and I thought that doesn't make sense anyway, but it doesn't come out anyway. So this is the right number. So here's how you do it. Basically everybody has a pre-shared key. So that's the number you put in when you go to a network and it says we are protected, so give me the password. And that password is something that the network manager can give you. Or you can have your own password, like in WUFI. In my home it is just one password that everybody, when the guest comes I will give it to them. So anyway, so the idea is that key and something from the AAA server that is combined to make a pairwise master key. So this master key could be combined in some way, or it could be just be there. But anyway, so the idea of combining 256-bit stuff is that if this case is more than 256, you hash it to 256, and this stuff is always 256 anyway. So you get a 256-bit pairwise master key, simply by R-ing. All right. Then the four-way handshake, which is going to come in the next slide. There is a four-way handshake during authentication phase in which both the sides, the supplicant and the authenticator, provide the nonce. Who is the supplicant? Yeah, the person coming in, the laptop coming in. So supplicant provides a nonce and the authenticator provides the nonce. Those nonce and the master key, these three items are run through a PRF, pseudo-random function. Through a pseudo-random function, and that produces a 384-bit transient key for WPA2 and 512-bit transient key for WPA. And then there is also something called group master key, which is set by the manager. And the group master key, so what is the group first of all? So there are some broadcast messages in the network which have to be encrypted, and everybody has to be able to listen to them. So there is a key for that, which is actually a shared key. Everybody, all stations on the network basically share that key. So that is the group master key. That is run through the pseudo-random function to produce a group temporal key. So this is basically, this is the key to be used right now for WPA2, and this is the key to be used for WPA. So in either way, and again I will have to check this number. I think this number is suspect, and this number 256 came from the book, and I have to check from some other sources. It could be 128-bit key, but it doesn't really make sense to me to use a 256-bit key for group protocol when we are using only 128-bit keys for. So I think both the numbers in the book are suspect. So anyway, so what happens is, so now you, how many keys you have? You have ePAL confirmation key, ePAL key encryption key, then you have temporal encryption key, and then you have MIC from access point, MIC from access point key, and MIC to access point key. So let me explain the meanings here. So when you do the negotiation, ePAL negotiation, you need some keys. And so those are these keys. They are used during that thing to actually, so there is a key confirmation and key encryption. So what happens is that you send the temporal key, you send the key that we are going to use, this, what we call session key, you encrypted in this ePAL key. ePAL key encryption key, right? So those are used just during that negotiation. And then during the transfer phase, you use these three keys. So this is used for encryption, and these two are used for MIC. MIC is the message integrity check. They are used for MAC, as we used to call them before, MAC, message authentication code, right? And there are two different keys for two different directions. If you're coming from access point, the messages coming from the access point have this key, messages going to access point have this key. All right. So all of these, so this is computed. Now let's see, 128, 128, 128, and 128. That is 512 plus 128. I don't know. Anyway, so, and here the same thing. In CCMP, which is the WPA2, we have the key confirmation key, key encryption key, same meaning as before, and the temporal key, which is used for CCMP, and this is group. Now, if you remember, CCMP is this chaining mode, and from this description so far, it appears that both of these use the same key, although these are two different encryptions, so you don't use the same counter there and same counter here. So this is a different counter than that counter. So this is the key which is used for both of all of these three purposes. Except here that the encryption is so strong that you really don't need three different keys, and this is AES, and so as opposed to here RC4. Anyway, and then you need a group temporal key, and again this is 128-bit key for the group broadcast, so I don't see why it should be 256 here. Okay, and I will have to check that. I will check that one. Let me write it down. All right. So now, it's a complicated picture, but is it clear to you what is happening? If not, please ask questions right now. There are so many keys being produced. Although all you have to do is one thing, which is that you have to have these two items, one from the AAA server and one pre-shared key. So all you just put in that some initial password or passphrase, and then it produces all these different keys. There are many keys here. The book has a table of these keys and the length and everything else. All right. But notice there is a PRF, pseudo-random function. So we'll talk about what is that PRF. So during the key management phase, the station sends the nonce. So this is A nonce, the station is A, STA, and its MAC address. Now here this is the problem. MAC is actually not message authentication code, is the media access control. So this is the 802.11 address. It is sent, sorry, A is access point, not a station, sorry. A is access point, so it goes this way, access point's address, access point MAC address, and the nonce. This is the station's nonce, station's MAC address. Both of these numbers are sufficient to produce transient key. So what is transient key? That is this key, PTK, pairwise transient key. Okay, and then that key is simply divided into 3 parts here and divided into 5 parts here. So if you add up 128, 128, 128, 64, 64, you get 512 bits. Anyway, so now you can generate PTK. Why can you generate PTK? Because all you need is the 2 nonces and this password. Once you have all these 3 pieces of information, you can produce those PTKs. So generate PTK. So now it says the station, the access point says PTK installed, and again this is my address and here's the MIC. So this is actually encrypted message. This is encrypted with this PTK, and this one says, look, now I have computed. So basically we have the same password, because if we had different password, then we won't be able to do that. So I know the PTK, and here is integrity check and all that, and so this is basically authenticates the access point, because if this guy knows PTK, it can verify that, and it will do the same thing. It will say, here's my address, and here is the authentication, the integrity check, and I know PTK also. Okay. At this point, once they both have authenticated each other, they can use that to exchange the GTK. Now GTK is the group temporal key, GTK. So this can send it and this can say fine, I got it. All messages are ePAL key messages, and ePAL key confirmation key is used to compute the MIC for the ePAL messages. So that explains what is this first key, confirmation key. So this is integrity check key and this is the encryption key. Now only thing which is bothering me in this diagram is that why are they using the same key for encryption and integrity, and I will have to check that too. I mean, it is strange that for ePAL messages they have an integrity key and the encryption key, integrity key, encryption key, integrity key, encryption key and all that. But when they come to this one, they have only one key. So we'll have to check that out. But anyway, all of these messages are ePAL keys, ePAL key messages. So now, this is another little bit of detail. ePAL has 5 or 6 different types of keys and different kinds of messages. While EAP had only, this one, 4 messages, request, response, success and failure. ePAL has ePAL key messages which are used for this, and then there are other types of messages which are not on this picture. So when we say ePAL key messages, the name is somewhat confusing because it looks like there is some kind of key there, but no, it's not, nothing to do with that, but it's just this is the type key. Okay, and so if you go back to ePAL slide, which I didn't put into this lecture, but it was in the previous lecture, there is a ePAL type and then there is a message type. Okay, so ePAL type is ePAL key. Some of you did this homework on ePAL, so you might know from there. There was a homework on Kerberos 4, something like that. All right. So data transfer phase. Now data transfer requires integrity and encryption. So they use TKIP for temporal key integrity, and the software change only to older for WAP, and it uses the 64-bit Michael message integrity code MIC instead of 32-bit CRC in WAP. So 32-bit CRC is replaced by this Michael, which is non-linear, and then encrypts MPDU plus MIC value using 128-bit RC4. All right, I think I can very safely change that 256 to 128 and in the previous slide, because it doesn't make sense to have, because basically you have only one hardware piece or one software module, so you are not going to have a different module for broadcast. And everybody understands why I changed this 256 to 128 bit? Because they are using that for encryption, and this encryption for the is encryption for the unicast packets, and this is the encryption for the multicast packets, right? So it would be very I mean, I would really think that they would not have 2 different algorithms for that. So they use 128-bit RC4, and they use MIC. Those are the only 2 changes. And they use, actually another change was that the key is now per packet key as opposed to previously it was master key. Then CCMP, which is RSN or WPA2, uses cipher block chaining for integrity and counter mode AES for encryption. Now PRF. So PRF is the pseudo-random function that is used to generate the nonces and the keys. and they use HMAC SHA-1 for all of these things. HMAC SHA-1. We already know what is HMAC SHA-1. It's just the detail is that to the input to HMAC SHA-1 there is a key, and then there is some input here, and that input consists of 4 parts. First part is A, second part is 0, third part is B, fourth part is a counter. All right. So K is the secret key. A is the specific text string. So they put a text string here, A. So for example, a text string is pairwise key expansion. So they will put those letters PAIRWISE space key expansion. Okay. That text string is put here in place of A. Binary representation of that. Then you put certain number of zeros, and then you use the specific, then again B is some specific data which is used in different keys. For different keys that is a different thing which will show you here in the detail, and that detail is in these formulas, and then there is a counter. By the way, B contains 2 parts, that data plus length, which will be shown in a minute. And let's see, so what else is that? Set counter to 0, and the desired number of bits from the left is less than 160. So then you get the number of keys that you need. Whatever it comes out, then you can get as many keys as you need. If and then if you need more than 160 bit, because hash function produces only 160 bit, if you need 512, as we saw here in the previous case, you needed 384 or 512, then you run it again. Put the counter again and run one more time. All right. So now let's see an example of this. So suppose you want to get PTK, right? And we use PRF for that. If you go back again to this picture, we are getting the PTK here for CCMP. We are using PRF. So this is the data which is specific to this case for this use of PRF. That is the one. And so let's see how it is put. So we say PTK is equal to PRF. Oh, actually, maybe I should leave PRM. I'm sorry, I should leave it PRM. I understand. So the PRF will only produce 128 bit, 160 bit. So PRM is basically the final result, which is many 128 bits combined to make whatever length you need. So anyway, so that is the function which is not PRF. This is basically the multiple runs of this. And in each run we will put this bit pattern here in A, we'll put zeros, and then we'll put this bit pattern in B. The bit pattern for B consists of minimum of the access point address and the STA address concatenated with the maximum of the access point address and the STA address, concatenated with minimum of A nonce and S nonce, concatenated with maximum of A nonce and S nonce. So everything is there, but minimum first, maximum later, followed by 384, which is the length in this case, specifically the length. So you put all that, and then you get, and you run it as many times as required to produce the PTK. Is this any question about this? Is it clear or confusing or what? Yeah. What is the 384? Yeah. 384 is the length. Okay, sorry. This 384 is the length of the output. 384 is the length of the output here. So now that's a good question, because I said here B is the use specific data and length. So now use specific data is this one, four inputs, 1, 2, 3, I see. Alright, so I was wrong there. So this is the length of the output, not the length of the use specific data. The length of the output is 384. For CCMP we need 384 bit key. Notice that 128 plus 128 plus 128 is 384. So this function will be run how many times? 160 bit is one time, right? So 2 times will give you 320. So you'll have to run it third time. 3 times, or 3 times will give you 480. Yeah, 480, and you will take 384 bits out of that. Yeah.
What's the O or 0 coming in?
Here, that's the number 0. Basically, that is used to make certain number of bits that you need for this HMAC input here. That is more like a padding in the middle. But this was interesting to me to see that they are using ASCII string as the input. And that's important, because for different keys they have a different ASCII string. Alright, so now this solves all the problem that we almost know of, almost all the problem that we know of. First of all, you cannot MAC address spoof. So previously the MAC address was in the hardware. In my days, actually, originally when we designed Ethernet, we designed it so that you cannot change your MAC address, and that was one of the design parameters of Ethernet, that the MAC address is fixed. But people started playing game, and now it is no longer fixed. It is in the firmware, and people can just change it by some simple commands. Your MAC address is changed. MAC address is a globally unique ID, so I mean you can become anything you want, right? So that means now you cannot do that with this algorithm, because it is included in the MIC and the CCMP MAC, both basically. So it is included in the authentication code. No replay, each message is sequence number. No dictionary based key recovery, all the keys are binary numbers, so you really have to do the whole search. You cannot do dictionary search. No key stream recovery, each key is used only once in TCAP, which is RC4, and here there is no key stream anyway. No weak key attack. So there were certain keys, if by mistake you selected those keys in WAP, you will be really in trouble. And so TCAP prevented that. TCAP prevented that by putting something byte in IV so that you never get a weak key. And then no rogue APs, so you could not have access points which were not company's access point, because there is a mutual authentication, and the access point may even provide certificate to verify that they are who they say they are. But what it doesn't address it is DOS attack, using disassociation or deauthentication attack. Management frames are still not implemented. 2 problems. So let me explain what those 2 problems are. So you can do a very easy DOS attack on any system, actually, it turns out. I was thinking last night about how you can give a hard time to somebody, and I didn't want to say it in the class, but since you guys are security people and you are white hats, hopefully not, you are white hats, not the black hats, whatever they call these things. So you can do a very easy DOS attack is that you go to somebody's account, let's say anybody's account, and you say I am this person, and you say password, you type any password. Second time you type the same password, third time the same password. What the system will do? Lock them out. Right? Now they have 1 hour job to fix it, because that person will try the right password and say, no, I forgot, maybe I forgot. Right? Yeah.
Since you can't track IP addresses because you can spoof your IP address, is there any way to effectively prevent a large-scale QoS?
Okay, so the thing is here, this is not large scale, this is very small scale by the way, but this is only 3 passwords you need to lock out somebody, right? So you can keep track of the IP address. The IP address is changed by the minute. So my IP address is this right now. If I go to my room, there's another IP address. So you cannot really, MAC address is the one that is globally unique, right? And little bit more reliable, except that now they're allowed to change. Right, so that also, person can say, well, this one not my MAC address, somebody else probably spoofed it. All right, so similar attack happens in the wireless. You can listen to somebody, if you know their MAC address, you can send a message saying that, sorry, bye-bye, I'm going. And you will be, and that person will be disconnected. Right? So that was the problem with WAP, and I am surprised that that problem is not addressed here. So that's an easy attack to give somebody a hard time. I mean, obviously they will reconnect right away or whatever if they want to continue, but you can disconnect them anytime you want. That's a disassociation attack. Okay, everybody understands what the attack is? Just disconnect message. TCP, you can send a TCP disconnect message, and that TCP will be disconnected. Similarly here, you can send a disconnect message for the wireless, and the wireless will be disconnected. You can, on the normal thing, you can just use any account, any password, anything for anybody, and they will be logged out. I mean, they will be logged out. All right. Second attack. Management frames are still not encrypted. Now, management frames probably don't need to be encrypted, but these are any accounting frames or anything, where you're sending either commands or something to anything. So basically, the management frames, as it is, so management is optional. It's not the data frames. Managements are optional frames where you send an SNMP message to an access point and say, well, tell me how many packets have you sent. Those are not encrypted, and those data can be still be basically faked. But it generally doesn't affect the operation. There might be, so here the way it is protected, because SNMP itself has an encryption in it. So when you send an SNMP message, the Wi-Fi doesn't encrypt it, but SNMP will encrypt it, right? So there is a protection there. All right. Now, the key point is that any of these attacks which are here, is it clear to you what that attack is? If it is not, then please ask right now. These are all attacks of different kinds. The only thing which I didn't explain is what is a weak key. And that was that will require a lot more detail of WAP, which I didn't want to go. But in WAP, if you selected a key which is not appropriate, then it will be very easy to break it. And so they avoided that by using IV. That ensures that weak key will never happen. Other than that, you should be able to understand what is a key stream recovery, what is dictionary based attack, what is replay attack, what is MAC address spoofing. Okay. All right, that finishes Wi-Fi. And any questions about Wi-Fi? So there are 3 modes. What are those 3 modes? WAP, right? You should not use WAP anymore. Second is WPA and WPA2. And basically we can use one of those 3. Let me see. We'll do it later on. But anyway, I wanted to check. I did check. A few days ago about Goofy, and I think it was WPA2. But anyway, yeah. So then there is another protocol called WAP. Now this is confusing. We are not talking about WPA. That is Wi-Fi. Wi-Fi is done. Now we are talking about WAP. WAP protocol is totally different context, total context switch in your brain. Now we are talking about how to serve HTTP to mobile devices. So about 10 years ago, they started thinking about how can you do web on your phone, right? And the main problem they faced was that the web pages are so big and the mobile devices are so small. How to fit a page on a device. So they came up with this solution called WAP. Okay? And so this solution is basically that the client, which in this case is a phone, sends a request which is captured by the gateway, which is called the WAP gateway, and this acts like a proxy, and then sends the request to the original server where the web page is. The web page doesn't know about mobile devices anything, so it sends a big response. Then this gateway understands the mobile device. It knows that your phone is a Samsung XYZ, and therefore it has only 3 lines and 5 characters each line or whatever. It knows all the phone devices. So it then makes the response suitable for your device. It's not an easy job, but they attempted that. So so that's basically it. This is gateway is the WAP proxy. And so there is basically the best thing would be that you write your own page for each device, which you can have another difficulty. I mean, how can you write one for Samsung, one for iPhone, one for that, right? So that's impossible. Then the proxy is designed with that, but then pages are all different kinds. How can you fit something which is so big into 5 lines? So that's also not very easy. So WAP actually, according to me, and I didn't see that written down in this book anywhere, WAP really didn't succeed. And I'm still going to verify that whether it really exists or we are just teaching some theoretical work here, because it was done 10 years ago. It was done 10 years ago, and I remember 5 years ago or 6 years ago going to a meeting where they said WAP is a failure, and now we are thinking about WAP version 2 and so on and so forth. And I don't know what happened. So anyway, so this book sometimes actually is out of date, and this could be the case. For example, I am preparing the next lecture, say, chapter 18, and it says, in future we will see this thing, and that future was a 1999 RFC. So 10 years ago, they were talking about that RFC, which was this says internet draft. So 10 years ago, they wrote that sentence, in future, and in a book which is 2011. So sometimes they forget to update it. Similarly, this WAP thing is I'm teaching you because it is in the book, but I really don't know whether it exists in reality or not. So anyway, actually this is more reliable, but I didn't see that here either, so that's why I prepared the whole lecture. So the best way to do is, nowadays people do it in the sense that nowadays many websites are designed for iPhone and iPod. All right, you go to any newspaper, coming to a question in a minute. You go to any newspaper, if they don't provide one for iPhone and iPod, they are not doing their job. In fact, I've been thinking if I get a minute, I will design my website for iPhone and iPod, because that's the only way people see the web these days, right? And so now there is some standardization coming in because of, and actually it's not really a standardization, but there is a majority. There's millions and billions of devices which have the same form factor, and then you get iPad and so on and so forth. So there is that kind of happening. So people are designing a special pages just for that. So that is one possibility. Yeah, question.
I was just going to say that WAP definitely exists.
Exists?
Yeah, like I worked on serving mobile ads this summer and we had to support.
Was it for a company?
What?
Was it for a company?
Yeah.
For which company?
Google.
Okay, so if Google is using WAP, I take it.
Supporting
It is supporting phone that has BAP, that have BAP. Okay, well, that's a good news. That's a good news. That satisfies my curiosity, because when I couldn't find this any such thing that it has been discontinued in this, I do remember IETF meeting, and that IETF meeting, if I remember the date right, was 98. 1998 IETF meeting, BAP people came, gave a presentation and said that, there is a problem, this and that, and it's failure. So BAP 2 is what they were talking about in that day, that year. But anyway, back to this. I think everything is said what is on this slide. Anything else? So we move on to the next one. So basically you have the server, you have a proxy, and you have the mobile devices. Now, only new box that we have added here is an HTML filter. So basically this BAP proxy can understand only WML. Just like HTML, we have WML. WAP, what is M? M is for markup language. WAP markup language, if that is already built in your web server, then this will have easy time. Otherwise, this will have to somehow convert your HTML into that kind of format. So that's why you need this device. Okay? So now we have a new word here in this slide, and that is WML. WML is like HTML, but only for little fonts. Second new word is binary WML. So WML and HTML are both ASCII, right? But every bit counts on the wireless. So they didn't want to send the bits that can be removed, and so they compacted it to a binary WML. If nothing else, you can just zip it and it becomes smaller by a factor of 2. So I really don't know what they do for binary WML, but that basically makes it smaller. For transmission over the wireless. So here is WML. Describes the content format for devices with limited bandwidth. So this looks like very much like HTML, but you put this thing there, bapforum.org dttwml.xml. So that gives you certain new codes such as cards and things like that. So WML, actually what you do is you put like a deck of cards, and each card is one screen full of the device. So you have this deck and the card, and you present them one card at a time, and each card looks like this. Card ID is main, title is first card, mode is wrap, and this is a sample WML page. So now if you write a web page like this, this is BAP compatible. Like that's what he's saying, that he wrote BAP compatible code for Google. Did you learn WML as part of that, or did you use WML?
I didn't do anything with WAP. I just know that I think it was pretty widely used.
Okay.
It's completely falling apart now. Like no one uses it anymore. We actually made a decision to stop supporting serving ads for WAP, but it definitely, I think,
Okay.
In countries other than the U.S.
Okay.
It's significant use.
Okay. All right. Good. But good thing is that if you put this is good win-win in the sense that it is not a lot of work for the web people, because they didn't put any device-specific thing here. All we said was that wrap it. If the device cannot support this whole thing line, then wrap that line. And then these commands would supply for any phone, and all the details will go somewhere else, basically in the BAP proxy. I think I should stop right here because there are a few more slides. So we'll continue here next time. Okay. And one more thing I wanted to remind was that there is this draft paper due Anybody knows when it is due?
Monday.
Eh?
Monday.
Oh my God. I should have talked about writing, but please read the rest of this project slides, because that's what I was supposed, maybe I should have done better than this. Hold on, I'm coming to your question. Is that there are lots of slides that say how to write and all that on the draft, so read those and follow those guidelines to write, so then you can have it on Monday. Next question, yeah, over there. What is your question?
What do you want to see for the projects on Monday?
Yeah, so I really want to see now the demo. I mean, in the sense that my personal demo, not the class demo, or something like that. So I want to see the code. I want to see being done somehow. And if something is not working,
The entire coding project should be complete on that.
well, this is what these guys are doing. So the writing people already have to write the paper. This is the final paper. They will be graded on this draft. Okay, so that's another thing is, on Monday when the people come, please bring 4 copies of your paper, hard copies, not soft copies, 4 hard copies of your paper, and 3 copies will be graded by the 3 students. So you get the grade on this. This is a major grade. That's not minor, basically. Major grade. So this is complete paper. The only thing is, this is complete paper, like the paper we submit to a journal. We submit our best paper, and then they say, no, still you fix this, you get one more chance to fix it, and you get one more grade after fixing it. But that first paper is what gets the major grade, first draft. So these guys who are writing the paper are submitting really the final paper. This is not, even though I don't know, I shouldn't call it draft. This is the final paper, except that now you will get one more chance to fix it when people give you comments. So the reviewers will give you comments saying that, no, this is not clear, this is not correct, this is bad, and then you fix it again. But those are only reviewers' comments. From your side, you should have done your best job. Yeah.
So do you just, for other projects, do you want to write up also, or do you just want us to demo the code with you?
Yeah, right. So basically, let me see. So these guys are being reviewed, and they are going to have 3 people review it. I have to find out the same way to you so that you will be reviewed, and then you will still get one chance to fix it. Reviewers, people will say, well, this is not correct, and maybe this is what we done, and you get second chance to fix it. So I think basically maybe we should do a class demo, and then get a code, get a grade from the people. Just like you get the grade. These guys are getting graded by the peers. You should be getting graded by the peers. Although I will have to think so that you only get 3 grades and not 18 grades or 15 grades. So I have to think about that, how to grade projects. But just to be on the same level, projects people are given 2 people at the same time, so they can write the code faster. But the deadlines and everything else is same.
So do we want to have a web page though for the
Huh?
project? We have to have a web page.
No, okay, so neither for the papers. Your paper can be written in Word document right now, this version. It could be anything. It could be whatever you want to write in. If you want to write in HTML, that is fine, but I won't see that HTML, because all I need is the final printout, which does not have any HTML in it. It's just basically a printout on a printer, right? So at this point, we will not check your HTML, whether it is a project or whether it is a paper. All right? I will just read the text, make a comment, and fix it. Once it is fixed, the next version will be HTML verified. Right? Okay, you have a question.
How long do you expect it to be?
Paper has to be 15 pages approximately.